First, let's recall how we are going to solve optimization problems. We start with draw and label. Then we have to find the equation. This is about the constraint. And we have to find a function to be optimized. Now we have to make sure that the function contains only one variable. So we are going to use the equation to reduce the variables in the function to be only one. Now we are going to think about possible values for the variable. This is the domain of the problem. And in any case, we have to find all the critical numbers in the set of the possible values. Now we have to show that indeed we have the absolute minimum or maximum as needed. If it's a closed interval, we are just going to use a chart and we are going to check all the critical numbers and the endpoints a, b. If this is an open interval, we are going to do the analysis of the first derivative and we are going to find the shape of the graph. Don't forget that the answer should require many times to have units. Let's now find the point on the line y equals 2x minus 1 that is closest to the point 4, 0. This problem can be simplified a lot by observing that minimizing or maximizing d distance is as minimizing or maximizing d to the power of 2. Instead of doing this, and you know that the distance is what? It's the difference of the x coordinates to the power of 2 plus the distance of the y coordinates to the power of 2 squared. This is just Pythagorean theorem if you recall. And one of the points is xy. This is the unknown point which is on the line y equals 2x minus 1. And 4, 0 is the other point. So I'm going to replace this by that. I want to show you why. This is always true because if a and b are positive and distances are never negative, so this is true. If a is less than b, then it's also applied that a to the power of 2 is less than b to the power of 2, but also if a to the power of 2 is less than b to the power of 2 and a and b are non-negative, then it's also true that a is less than b. I can show you that. Because a and b are non-negative, and let's assume in this case that they are even positive, then if you have two lengths, line A has length of A and the other one has a length of B, then we are just going to build a square on those lines. And you can see immediately that the square that is built on the longer side, which is the one that is green here that has an area of b to the power of 2, is more than the a to the power of 2, which is the square built on the shortest one. So because this is always true when a and b are positive, we can assume that d is positive, so we can use that. So here is a good drawing. We don't need really to sketch the line. We just take a point and realize that this point is on the line, y equals 2x minus 1, and the point for 0. And we need to minimize the length of this green line, which is d. So what is the equation? We have first like two variables, x and y, but because y and x are both on the line y equals 2x minus 1, we know that y equals 2x minus 1. This is the equation. What is the function to be minimized in this case? We will take d to the power of 2, as I explained before. And we get that. Let's simplify that. So instead of y, we are going to write 2x minus 1. We are going to square everything. Okay, and we are going now to use that. And finally, we have one variable only. We are going to simplify that. And we get this quadratic of 5x to the power of 2 minus 12x plus 17. What are the possible values for the variable? Well, the truth is that x can get any value that you just want. It means that this is an open interval problem. So now let's find critical number or numbers. Well, we need to differentiate this. And if you look at the function that it's written above, we get 10x minus 12. We want this to be 0, so x equals 1.2. Now we want to show that this is really absolute minimum, so we want to look at the shape of the graph. So let's use the first derivative test first. So here is the analysis of the first derivative. It is negative when x is less than 1.2, and it is positive when x is more. So the function is decreasing and then increasing. And here's the shape of the graph. When you look at the shape of the graph, it's clear that there is an absolute minimum when x is 1.2. So let's answer. We need the point. So what is this point? Well, the x coordinate is 1.2, and then we will substitute to get the y by doing 2x minus 1, and we get 1.4. Let's now find the dimensions of the maximal area rectangle that can be inscribed in the area under the parabola y equals 4 minus x to the power of 2 and above the x-axis. A good picture, it's a must, so here's a good picture. Here is the parabola y equals 4 minus x to the power of 2. And here is an example of one such rectangle which is inscribed in the area under the parabola and above the x-axis. You have to be very careful now with the dimension of these rectangles. Well, first of all, note that if this point is xy, and it's all depend on this point, then what is this? If this is the point xy, this is actually 2 times x. And this is easy, this is just y. So each point in the first quadrant has a matching point in the second quadrant. So we can restrict the point xy to be only in the first quadrant. Look at the picture, this point xy has also a matching point in the other quadrant, that if you take this point, then you can inscribe a rectangle via this point. Here is this point. This point is negative xy if the other is xy. So there is no need to do this problem like that. I want really to restrict the domain. It's going to help me a lot by saying, you know what? It is enough to pick a point in the first quadrant only. We can also maximize half of the area. In this case, xy will be a point in the first quadrant. We will not do this, but we will maximize the whole area. It's much more difficult to actually maximize the whole area than only half of the area, because it's more confusing algebraically. I'm not going to do 2 times maximizing on the first quadrant, but I'm going to maximize this as it is. Let's find the equation. Well, this is not just the point xy. The point is on the parabola, which means given a given x, there is only one y, and this is 4 minus x to the power of 2. So y equals 4 minus x to the power of 2. This is the constraint of the problem. What is the function? This is easy. This is just what? the area. Look at the picture. The area is 2 times x times y. We are going to get rid of one of the variables. If a equals 2x minus y, I'm going to use the fact that y equals 4 minus x to the power of 2 to get rid of y. So we are simplifying the algebra and doing, all the necessary algebraic steps, and we get that the area is 8x minus 2x cubed. What are the possible values for the variable x? Because x is in the first quadrant, it cannot be negative. But also, x is an x-coordinate on this parabola, and when you look at the picture, you can see that x cannot exceed the value of 2. So x is greater or equals to 0 and less or equals to 2. Let's find the critical numbers. Let's differentiate, and we want this to be 0. Solve. So algebraically speaking, I'm getting 2 answers here. But one is negative, so I have to take this away. The only one in my domain, 0, 2, is x equals square root of 4 over 3. Now I want to show that this is really the absolute maximum. This is a closed interval problem, so it's pretty easy. Let's do the chart. In the critical, I get something that is not 0, and actually it's more than 0. It is positive. You can see that it is positive because this number to the power of 2 is less than 8. So 8 minus x to the power of 2 is positive, and also x is positive. When you plug 0 or 2, you get 0. So it's very clear that indeed there is an absolute maximum when x equals square root of 4 over 3. Now you want to answer the question, and when you read, you have to find the dimensions. So this is only x, so let's find the value of the y. When x is this, then because y equals 4 minus x to the power of 2, we get that y is 8 over 3. The maximum area rectangle is when its length is what? Look at the picture. The length is 2 times x, so it's 2 times square root of 4 over 3, and its width is 8 over 3.